Welcome back to the Flow of Ikigai. In our last video, we talked about avial trees. That's completely about nonlinear too. But in this video, we are talking in another section of nonlinear structures, which is called Dijkstra algorithm. So when it comes to linear structures, they are like sitting neat lines and straight lines. Everything just set on a straight line neatly. So it's all about linear structures. So today we're going to cross over nonlinear structures about graphs and to solve the one of most famous problem in computer science, which is pathfinding. If you have ever used Google Maps, fast drive home from your destination, or internet sends the data packets through multiple traffics in milliseconds. So how do these things work actually? And then you are looking at pathfinding. The main engine behind this Dijkstra's algorithm. So let's look at the map on our screen. So Dijkstra's algorithm is a legendary method for finding the absolute shortest path from a single starting point to all other connected points in a network. So, but how does it actually know which way to go to without checking every single road? So we have to look at step by step. So we will look at that, and as you can see, there are two concepts, which is age weights and distance updaters. To find the shortest path, Dijkstra relies on two simple concepts, which is age weights and distance updaters. So age weights simply means every line connecting our cities has a weight, and you can think of like this. At this time it takes to drive down that road, or the toll fee you have to pay. Our goal is to find the route with the cheapest total toll, right? So nobody wants to get the expensive toll right here. They just want the fastest route as they want to get the cheapest toll. And the second one is distance updaters. So it simply means distance updaters, or what computer scientists call relaxation. So look at the title badges next to our nodes. This is our ledger. And initially we don't know how far anything, so algorithm assumes it's cost infinity to get anywhere. So and as we explore the map, if you find a cheaper route to city, we relax and infinity and update the ledger with the new lower price. So this is the example for the next step, and this is a stepwise example. So let's see this in action. And we want to create a route from city A to city D. And how do we do this? We have to, there is a golden rule in Dijkstra's algorithm that is greedy. And that is greedy. It will always pick this unvisited node with the cheapest known cost, explore its neighbors, and then lock it in forever. So we will start from A. So as you can see, and we begin with node A. It costs us 0 to stand exactly where we already are. Okay, and so A is our current active node, and so it's just check the two paths, and we explore from C right here. And yeah, so from A we look at our options. We can go to B. So we can go to B for a cost of 4, or C for cost of 2. So which one is shorter path? Oh, this one is shorter path, right? Okay, and averages B and C update immediately. So now is fully explored. Now we mark it green and locked it in. So now the greedy rule kicks in. In all our unvisited cities, which one is the absolute cheapest right now? Which one is it? So it's C at cost of 2. So we move to C because it's the cheapest one here. It still exists. It's the cheapest one around across the all routes. So the weights update is as the cheapest one, and we have to move through that nodes. So for now, we have to explore from B, and we click explore from B, and yeah, that's coming up. So we are standing at C. So now think we are standing out now C. If we look at D, it cost 5 to get there from here. 2 plus 5 is 7. There is 7, and it cost so much. So we update D is ledger from infinity to 7. But look at B. We previously thought it cost 4 to get B, but if we go through C, it cost only 1. See here, that cost only 1. So in our total now is 3, but this one is cost 7. So we override the ledger. This is the magic of relaxation. Now C is locked in. So now we have to target D reached. So yeah, from B we have to route the left to D, okay, and the cost is 1. And our running total is 3 plus 1 with equals 4. So since 4 is cheaper than our previous record 7, we update D as last time. So this is the example of Dijkstra's algorithm, how it works behind the scenes, and how it routes through the weight updaters. So there is a trap which is called negative weight trap. Now you might be wondering, what if the road pays you to drive down it? What if weight is negative? Dijkstra actually fails if there are negative weights. So that's the only trap when we doing works with Dijkstra's algorithm. So remember, Dijkstra is greedy and assumes that adding more roads can only increases your total cost. Look at the visualizer. If we start at A, Dijkstra sees B as cost 2. It means Dijkstra sees B as cost 2, and the C cost 5. Okay, now you got it. It greedy locks in B because it's the shortest path, the cheapest one. It's greedy. So Dijkstra sees B cost 2 and C cost 5. It greedy locks in B because it's looking for the cheapest route and the most shortest path, and thinking 2 is the absolute best it will ever get. But it completely misses that taking the long way A to C and then taking negative 4 to back to B, and it's actually cheaper because it already permanently locked B, thinking that is the most cheapest way to get there, and it refuses to lock back. If you have negative weights, you have to use a different algorithm like Bellman-Ford. Yeah. Well, now I think you have get the exact idea about this, how it works and how it moves through the negative weights. And so we're looking at the code implementation. How do we actually write this elegantly in Java? The secret is using a priority queue. You know what is priority queue? Think of like priority queue is like a smart basket. Every time we update city's ledger with the cheaper cost, we write the city's name and its new price on the sticky one and throw it to the basket. And the basket automatically rearrange itself so that the absolute cheapest city is always for floating right at the top. So look at the code right here. Now node current is peq.poll. The single line reaches into the smart basket and grabs the cheapest node, and then we have to loop through this using a for loop. Then we have to loop through its edges. If new dist less than equal dist age to, it means This is a current relaxation. If the new distance cheaper than our ledger, we update the ledger and add a new node to the basket. So that's really simple, right? So this is all you want to know about this code implementation. This is just an example that we used from priority queue in Java framework, and we implement just a single Dijkstra algorithm using 2 nodes. So it is an elegant, incredibly efficient thing in modern software navigation. So when you use Google Maps or something that you try to navigate on, that's mainly behind engineers' Dijkstra algorithm. If this visualizer helped you to understand this concept better, just drop a like and just let me in the comment if you have got any problems of this. And keep coding, stay calm, and I will see you in the next one. Thank you for watching.